the virtual classroom of Chem-based School of Chemistry. Can you hear me? Sound clear? This discussion will be the 2021 October and 22 Jan paper 6. To begin with the October paper. This question is about copper and some of its compounds. 2 tests were carried out on separate samples of aqueous solutions of copper 2 sulfate. Few drops of aqueous sodium hydroxide were added to a sample of copper 2 sulfate solution. State what you see. You see a blue precipitate. You can say just blue precipitate, or to be more specific, pale blue precipitate. Few drops of concentrated hydrochloric acid were added to another sample of copper 2 sulfate solution. More of the concentrated hydrochloric acid added until it was present in excess. Describe the changes that would be observed during this test. Now, this copper 2 sulfate, when you add the hydrochloric acid, it forms at last the tetrachlorocuprate, which is CuCl4 2-. That's the final product. That is when you add in excess, all of copper 2 sulfate turns to this tetrachlorocuprate. Now, tetrachlorocuprate is yellow color solution, whereas copper sulfate is a blue solution. Right, so the blue solution turns yellow. Right, that's the observation. And but you have noticed there are 2 marks given. So we have to also explain what happens, the intermediate color change. Now the blue to yellow is not a, at once all of blue will not turn yellow at once. When part of the blue turns yellow, the yellow will react with that. I mean, yellow along with the blue, the remaining blue, the yellow form and the remaining blue will give you the green color. That's the intermediate color which is seen. So the blue color copper sulfate turns green and then turns yellow. Green is not a special different compound. It's basically when part of the blue turns yellow, at least half of it, then the half of the yellow in the presence of half of blue will give you, or you will see the solution mixture as a green color. So blue copper sulfate turns green and then it turns yellow. Right? So there's no precipitate here. The solution will change its color. Describe a test and its positive result to confirm the presence of sulfate ion on the sample of copper 2 sulfate. You add barium nitrate acidified with nitric acid. Get a white precipitate of barium sulfate. Or you can use barium chloride acidified with hydrochloric acid. Get a white precipitate of barium sulfate. So either barium chloride or barium nitrate can be added. But if you're adding the barium chloride, the corresponding acid should be added, which is hydrochloric acid. That is added after adding the barium chloride. Or if you're using barium nitrate, you should add nitric acid. That is after adding the barium nitrate. After adding barium nitrate, you should add nitric acid. The reason for adding of acid is to remove the 2 other barium precipitates which are white. Like barium sulfate is white, barium carbonate is also white. Like barium sulfate is white, barium sulfide is also white, BaSO3. So by adding the acid, the carbonate and the sulfide reacts with the acid. The white precipitate is due to the carbonate or sulfide, it will dissolve. But white precipitate due to barium sulfate will not dissolve. So simply you're confirming that it is sulfate by adding the acid. Electrochemical cell was made from the electrode systems represented by these half equations. Calculate the E cell for the electrochemical cell. Now, which one to be reversed? The more positive, the less negative half equation should be written as reduction. This is iron 3 plus iron 2 should be written as reduction, more positive one. Less negative one should be reversed. So you have to reverse this one. Less positive, the more negative one, right? So when you reverse it, that becomes a oxidation half cell. E cell equals E cathode minus E anode. Cathode is red cat reduction, which should take place at the cathode, so 0.77. The more positive one is what undergoes reduction, minus 0.34. The less positive one is the one which undergoes oxidation. So this is overall positive value. The reaction is feasible. This is the electrochemical cell. The iron, which is reduced, reduction half cell is done on the right side reduction, left side oxidation. Platinum wire. This is a problem here. Platinum wire is an issue because to be a salt bridge, there are two or few mistakes here. One is that you have to use salt bridge here, filter paper soaked in potassium nitrate. And the second mistake is that the electrode should be fully immersed in the solution, fully immersed. And we have to use a high resistance voltmeter. High resistance voltmeter. This also takes, not mentioned about high resistance voltmeter, right? Identify 3 mistakes in diagram and the changes needed to correct them. So mistake number 1 is what? The platinum wire is used instead of the salt bridge. Platinum wire is used as an obvious mistake instead of the salt bridge. What's the correction? Filter paper soaked in potassium nitrate should be used. Filter paper soaked in potassium nitrate should be used. And second mistake is that low voltage supply is used. Second mistake, low voltage supply. And the change, you have to use a high resistance voltmeter. High resistance voltmeter should be used. And of course, the dipping half is not a big mistake. You can do this with the half dipping. Usually we dip half when you have equilibrium between the gas and the solution. So it's not an obvious mistake, but you can see here is a solution containing mixture of ions, Fa2 plus and Fa3 plus. When you have a mixture of ions, then the electrode should be platinum. So this is the nature of the electrode. The ion should be replaced with platinum. Ion should be replaced with platinum, right? So even it is half immersed, still the electrode potential, the half system, half cell will work. Right, it won't work, right? So that's not a half exposed and half immersed is not an obvious mistake, right? It's not a mistake, still it works. So the obvious mistake is that the iron electrode should be replaced by platinum. Iron electrode is used is a mistake. Correction, it should be replaced with platinum. Replaced with platinum. Brass is an alloy of copper and zinc. A student to determine the percentage of copper in a sample of brass. Procedure is mentioned. Weigh the sample of brass, place the brass in a beaker, and add concentrated nitric acid until all the brass dissolves. Nitric acid reacts with zinc easily, and it also reacts with copper, but the zinc is a displacement reaction. Hydrogen is displaced, but the copper is a different reaction. Nitrogen dioxide and copper nitrate is produced, not hydrogen gas. Transfer because reason is copper is below hydrogen in the reactivity series. Transfer the solution and washings to a 250 volumetric flask. Make the solution up to the mark with distilled water and mix well. If at 25, that means 1/10 of the original solution, 25 of the solution into a conical flask, neutralize the excess acid in the solution. That means you carry out titration by titrating with the alkali, that is to react with the excess acid. Add 10 centimeter potassium iodide solution to the conical flask. Titrate the iodine produced. Of course, potassium iodide in the presence of acid will produce iodine. So that iodine, because copper reacts with the iodide ions to produce iodine, and that iodine will react with the potassium iodide, will react with that and produce iodine. And that iodine will react with sodium thiosulfate solution. So we use starch as the indicator. Starch is added when it's very close to the endpoint, and the color change will be the color change from blue-black to colorless. Because iodine forms a blue-black complex with starch, at the endpoint it turns colorless. Repeat the titration until concordant titers are obtained. That's the titers which differs by 0.2 or less than 0.2. Copper and zinc both react with concentrated nitric acid to form metal nitrates, nitrogen dioxide, and water. Write the balance equation for the reaction of zinc with concentrated nitric acid. State symbols not required. So this is normal acid metal reaction, which gives salt and hydrogen gas. Salt and hydrogen gas. This is concentrated nitric acid, zinc nitrate, and the hydrogen gas. The thing is, now the question arises because it's concentrated. Is there any further reaction possible? We have to think about that as well, because that can be. The data booklet is not given here. Because sometimes, like for example, with copper, you get nitrogen dioxide and water as well, right? Nitrogen dioxide, water as well. So that's possible with copper. Name the most suitable piece of apparatus to measure the 10 cm cube of potassium iodide solution. Now, to measure this 10 cm cube, you can use a measuring cylinder, because accuracy is don't decimal places here, right? It's just 10. This 10.0 is the pipette. 10.00 is the pipette. So here it's mentioned as just 10. Measuring cylinder can be used, and also it is in excess, so accuracy is not the issue. Here it says potassium iodide is in excess, so that's why I just take 10. So you no need to be accurate there, because it is already used in excess. State at what point the titration the starch solution should be added. Starch should be added when the solution is pale yellow, because the reason is the starch iodine complex is the insoluble complex, right? So at the beginning, if you add starch, like any other titration we add at the beginning, the indicator, what happens, the iodine concentration is very high, right? So when the iodine concentration is very high, what happens is that the starch iodine complex concentration will be high. And that's an insoluble complex. That's an insoluble complex. So in that case, what happens? The concentration of the insoluble complex is very high. Therefore, thiosulfate will not be able to react with the iodine well, because that complex is highly concentrated, right? So that is why we add the indicator when it is very close to the endpoint. That means the yellow-orange or the yellow-brown solution of iodine, it becomes pale yellow. That is the point where we add starch. So at the endpoint, the blue-black complex will turn colorless. So when it's pale yellow, we add starch. That's the reason I mentioned. Only copper 2 plus ions in the solution react with the aqueous potassium iodide, not the zinc. So it produces iodine, and this produced iodine is what is titrated with the thiosulfate. So the amount of iodine which is produced is the amount of iodine which is reacted here. Actually, it's the same amount because the amount of iodine which is reacted is what is titrated with sodium thiosulfate. So the mass of the brass sample is given, the mean titr of 0.1 sodium thiosulfate given. So you can easily find the moles of sodium thiosulfate. Then you can find the moles of iodine, moles of copper 2 plus can be found. You know the moles of copper 2 plus, the mass of copper can be found. Then you can work out the percentage mass in the brass, because brass is a lot of copper and zinc. And then don't forget the solution is in 25. So once you finalize the entire, because the entire brass is dissolved in 250. So to find the number of moles in 250, you have to multiply by 2. So first step would be to find the number of moles of thiosulfate. So 1000 contains 0.1, 28.60 contains 2.86, 10 to the power minus 3 moles. Now can find the number of moles of iodine. That will be half of this. This number of moles of iodine is half of that, because 2:1 ratio, 2.86 10 to the power minus 3 divided by 2 is 1.43 10 to the power minus 3 moles. So now the moles of iodine is known. You can easily work out moles of the other species, which is the moles of copper 2 plus. Right? It is twice the moles of iodine. The moles of copper 2 plus in 25. Again, 1.43 10 to the power minus 3 times 2. 1:2 ratio. So it will be 2.86 10 to the power minus 3 moles again. And that's the moles in 25. But our original solution is in 250. Therefore, number of moles of copper 2 plus in 250 ml will be 10 times of this, which is 2.86 10 to the power minus 2 moles. That's the moles of copper 2 plus. We can now find the mass. Multiply this by the molar mass, because moles of copper is the moles of copper 2 plus as well. Multiply by 63.5. We get the answer as 0.18161. So we can write as 0.182. That's the mass of copper. We can take the exact mass as well. 0.1818161. So percentage mass. This mass is present in how much of total mass? 3.9%. 4.656%. 4.656 means 657. Now specify the appropriate number of. So whenever it says appropriate number of significant figures, or at least 3 significant figures, we should give the answer. Clear? Oh, yes, mass of copper. Let me check. I think I did a mistake there. Calculation 10 to the power minus 2 times 63.5. Yes, you're right. Put the decimal at the wrong place. It should be 1.8. 46.7. Appropriate number of significant figures, meaning 3 significant figures is sufficient. Clear? Any questions there? Right, that's the question number 1. Two organic compounds A and B are colorless liquids. Each compound contains only one functional group. Just important note is that means once you identify that specific functional group, that means you're done with the test. 2 tests were carried out on A. The observations for each test was recorded in the table. Complete the statements in the inference column by writing the names or formula of the functional groups. A few drops of A were added to 2 centimeter cube of 2,4,2-DNP, which is Brady's reagent. Orange precipitate. Brady's reagent, orange precipitate is given for aldehydes or ketones. So functional group can be aldehyde or ketone. Aldehyde or ketone functional group. Can you write the formula? Names or formula? Yes, you can write the formula. A few drops of A were added to 2 centimeter cube of palings. Get red precipitate. That means the aldehyde is confirmed because palings and Benedict's and palings is same as Benedict's, but Brady's is different. Brady's is 2,4-DNP. So don't confuse between Brady's and Benedict's. Benedict's is failing. Brady's is 2,4-DNP. And likewise, it will be active tolerance as well. Get silver mirror. Give the formula. The red precipitate is copper 1 oxide. 1 oxide is the red precipitate form. Simplified mass spectrum of A is shown. This is A is what? Aldehyde, right? Aldehyde, which has a mass charge value of the molecule ion being 58. It is 58, right? And here we have peak at 31 as well as a peak at 29. Let's see later on. Here's the formula of the one of the ions responsible for the peak at 29. What can the P29? Aldehyde. Can this be 29? The functional group. Let's see. 12 carbon, 16 is hydrogen and oxygen, and 1 is oxygen. It can be 29. This is one possibility, right? Or you can also write a CH3, CH2. That's well-known group for 29, right? CH3, CH2. There are 2 possibilities here, right? We have to write both. We can't just write one. This or that it can be. A contains one functional group with the mass to charge value of the molecule ion and the structure of A. Mass to charge value of the molecule ion is 50. You can easily see from the mass spectrum. The highest mass to charge value is the molecule ion, which is 58. So what is the aldehyde with 58? So if you have aldehyde group, that's 29. C2H5 group is also 29. 29 plus 29 is 58, right? So structure of A should be propanol. Propanol. So C2H5 group give you a mass to charge value 29, and the aldehyde group also will give a value of 29. Yeah. So it's propanol. 2 tests were carried out on B. Complete the statement in the observation and inference columns. 2 drops of B were dissolved in 2 centimeter cube of water. 2 drops of universal indicator were added to the solution. Solution is alkaline. So alkaline means the universal indicator will turn blue color. Because, see, beginning it says what? Colorless liquids, one functional group. A is a aldehyde, and this is all about A. And B is alkaline. It can be blue color, blue. Even if you write as purple, that's fine because we don't know. The strong alkali, it's purple. Strong alkali, it's purple. Weak alkali is blue. So either blue or purple can be written. B was added drop to aqueous copper 2 sulfate until B was present in excess pale blue precipitate form with the first few drops of B. That means your B is alkali. B is alkali because alkali reacting with copper sulfate, you get a blue precipitate, right? And you add excess, see what happens. Deep blue solution is formed. This is ammonium. Ammonium hydroxide, right? Ammonium, yes, ammonium. But this is, we can't say ammonium hydroxide because it says organic molecule, right? Organic molecule at the beginning. I remember something like that. If one functional group. One functional group. Yes, two organic compounds. So it has to be, it can't be ammonium hydroxide. There's two organic compounds. So then ammonium hydroxide, which organic compound gives a similar observation to ammonium hydroxide? Diamines. Diamines, right? So the functional group is amine, NH2 group. Functional group is an amine. Because amines behave just like ammonia. So when you add copper sulfate, get a blue precipitated copper 2 hydroxide, excess, it dissolves to form a deep blue solution. Tetramine diac or copper 2 plus complex. B has a molar mass of 59 structure for B. So NH2 is 14 plus 2 is 16. So you can now put some CH2 groups. Let's see, how many CH2 groups? Just put 3 and see first. 3 times 12 is 36. That can't be 4 because 4 is 48, right? So 36 for carbon. Nitrogen is 14, and you add the hydrogen at last. 5, 3 plus 2, 5, 5 plus 2, 7 plus 2, 9. You get exactly 59. Structure is this. You might now ask me, how do you know it's a linear structure? Can't that be a branch structure like this? This is also correct. Because the reason we don't know there's a linear or a branch structure, so you can have two answers for this. You can draw a linear one or a branch one. Right? That's question number 2. Everything is clear there. For the clarification. But quite straightforward and easy paper compared to the previous ones. A student carried out an experiment which determined the enthalpy change when solid lithium chloride dissolves in water to form a solution. This was prepared to replace 25 of distilled water into polystyrene cup. Measure and record the initial temperature of water at 2.12 lithium chloride to the water. Stir the mixture and record the highest temperature reached. Give a reason why polystyrene cup is used instead of glass beaker, which is a good insulator. Minimize the heat absorbed by the beaker. Good insulator. The temperature rise is 12.5. Calculate the enthalpy change for the formation of this solution, lithium chloride. include the sign, and it's in your answer. So Q equals MC theta, can be used, delta T. M is mass of solution. The mass of solution is 25. 25. Heat capacity is 4.18. Temperature change is 12.5. So 25 times 4.18 times 12.5 is 1,306.25 joules. In kilojoules, 1.30625 kilojoules, right? Question is to find the enthalpy change. We should divide this delta kilojoules per mole by the moles. Find the delta Q over moles. Moles of what? Moles of the limiting reagent here. You have just 2.12 lithium chloride. So first find the moles of lithium chloride, mass over molar mass. Lithium is exact values you need to get, 6.9. And chlorine is 35.5. So this is 42.4. 42.4. So 2.12 divided by 42.4 is 0.05. So the Q in kilojoules divided by the moles. 1.30625 divided by 0.05 is 26.125 kilojoules per mole. And the sign is important here, and it's exothermic reaction. If you don't put the sign, you will lose a 1 mark because temperature rise, it says. Temperature rise. That means the reaction has to be an exothermic reaction. Clear? Thermometer used to measure the temperature change had uncertainty of plus or minus 0.25 for each measurement. Calculate the percentage uncertainty in the temperature change in this experiment. So that's the error. Percentage error is the uncertainty, or the error should be multiplied by 2 because they're taking 2 readings over the value into 100%. Right? Value is 12.5. So 0.25 times 2 divided by 12.5 by 100, you get a percentage error of 4%. Percentage error of 4%. Temperature rise in the experiment was low. And which ones you to multiply by 2? Pipette, we don't multiply. So you take only 1 reading. Measuring cylinder, we don't multiply. Take only 1 reading. Volumetric flask or graduator flask, you don't multiply. Pipette, burette, you had to multiply by 2 because you take 2 readings. But then thermometer, initial temperature, final temperature, 2 readings. Even the weighing scale, initial mass, final mass. Temperature rise in this experiment was lower than expected due to the heat loss to the surrounding. Decide the changes to the procedure that would give more accurate temperature rise. Include a stopwatch and details of a graph in your plot. Right. Of course, you can carry out a reaction. You can use a lid to minimize the heat loss. The thing is, more than that, to be more accurate, if you remember, we have discussed that plotting a graph. This is zinc. What is this reaction again? Yes, dissolving of lithium chloride in water. So what you do is you can record the initial temperature, right? Record the initial temperature, and then every few seconds record the temperature. You can say add the lithium chloride, record the initial temperature for the first few seconds, right? If you remember the experimental technique which we have done, the practicals for the AS, you've got 2 minutes. we record the initial temperature, and at specified time, maybe at 2.5 minutes or 3 minutes, you add the zinc, right? Add the zinc at maybe 2.5 minutes or 2 minutes, that's fine, any specified temperature. And then you record the temperature every 30 seconds or every 1 minute for next 5 minutes. And you plot a graph for temperature against time. Right? So what you get is you get a graph like this. You can just draw a rough sketch as well. Is the temperature in Celsius? The time, right? The independent variable is time. Temperature in Celsius. Why the time is in the x-axis? Because we are studying, we analyze the change in temperature with time, right? So initially, you take initial reading, say about for 2 minutes, 0, 1, 2, right? Now on the third minute, you can add the zinc. Don't take the recording at the third minute. On the fourth minute onwards, every minute you take the recording. You can take every minute or every 30 seconds. So the fourth minute onwards, you take the recording. So you get a graph like this. So you draw the best fit line. Then this up to the third minute where you add the zinc. And draw a vertical, perfectly vertical, not slanted vertical line. And this will give you the delta T. This is actually not the, this is a experimental, not this is a theoretical temperature rise. As to the theory, temperature rise should be higher, right? Experimental temperature rise is over here. You might ask me now, why did you plot this graph? Why can't you just take the maximum and the initial temperature? Maximum minus initial, you can get the temperature change. The reason is we plot this graph to minimize error, especially the heat loss. That error can be minimized here because you draw a cooling curve. This part of the graph is known as the cooling curve. So there's a pattern of cooling. So when you extrapolate this and you connect this to the point where we add zinc at the third minute, you can get the experimental, theoretical, actually the theory temperature rise. Theoretical temperature rise can be taken. It will be much better, greater than the experimental temperature rise. Yeah. So you basically have to explain this whole process. Can mention this first. Since it's 5 marks, details should be mentioned. You can first mention, record the initial temperature of water. For the first 2 minutes, every minute for the first 2 minutes. Every minute for the first 2 minutes. And add lithium chloride at the third minute. It can be any minute, it doesn't matter. You can even add at 2.5 or 3 or 4, but initially if you take about 2 or 3 readings initially, 0, 1, 2 minutes, third minute you can add lithium chloride exactly at the third minute. Stir the mixture and record the temperature every minute for another 5 minutes, for example. Every minute for another 5 minutes, it's up to 8 minutes. For the temperature of the mixture every minute for another 5 minutes. And plot a graph of temperature versus time. And maximum temperature change can be found. Maximum temperature change can be found. as shown in the below graph. Here, final question. Question is about alkaline hydrolysis of ester X. X is alkaline benzoate, alkyl benzoate, alkyl group here. Be represented by the formula C6H5CO2R, where R is alkyl group. The hydrolysis equation is given. Measure 5 cm cube of X and pour it into a pear-shaped flask at 25 cm cube of excess aqueous sodium hydroxide solution at few anti-bumping granules. Now, excess sodium hydroxide is added to ensure the complete hydrolysis, and anti-bumping granules is added to ensure smooth boiling because it increases the surface area and prevents the formation of large bubbles. Heat the flask and contents under reflux because the reactants are volatile, so reflux should be done. Allow the apparatus to cool and then rearrange for distillation. Distill the mixture, collects about 2 centimeter cube of distill the mixture and collect about 2 centimeter cube of the alcohol ROH. Allow the pear-shaped flask to cool, pour the contents into a beaker and add excess dilute hydrochloric acid. This is important because the reaction is exothermic. It's important to cool before you add the acid. Impure benzoic acid form as crystals in the mixture. Recrystallize of benzoic acid using water as a solvent. We know how to do that. The 5 steps. Weigh the dry crystals and determine the melting temperature. Student drew the diagram of the apparatus set up for distillation in step 3. There are 3 errors in the diagram. The main errors here, let's see. Thermometer bulb should be in the same level as the distilling knob with thermometer bulb. And the whole apparatus should not be kept sealed. Okay, the whole thing is sealed. You should connect this to film. We're going to have a receiver adapter here right, for the fume carpet. Third is direct heating has been done. Direct heating has been done. Right? And also it says pear-shaped flask, right? You know, use a pear-shaped flask. This is not very effective because pear-shaped flask, the heat distribution is even. Here it's not even. Right? Yeah. How about the heating? Now, they haven't mentioned of direct heating here. Direct heating is not just heat is mentioned, so there's nothing wrong in that. That's not a point to mention because it just say heat. We don't know how the heating is done. But if they said direct heat, then it's wrong. Right? And also in the procedure, it's mentioned as indirect heating. So how direct heating is done? Just hold the Bunsen burner directly. Directly hold the burner. Right? That's direct heating. The first mistake you can mention the entire apparatus is sealed. Right? So this will result in pressure buildup. correction should be you can keep remove the bung in the receiving end, the receiving tube. You can remove the bung, or can attach a receiver adapter and connect it to the fume carbon. If you feel that products are toxic, you can say remove the bung at the receiving end, or attach the receiver adapter and connect it to the fume carbon. Second, you can say thermometer bulb should be in the same level as the distilling arm or the condenser arm, side arm, you can say. Thermometer bulb should be in the same level as the condenser arm or distilling arm. Third, conical flask has been used instead of the pear-shaped flask. Where is a conical flask? Correction is pear-shaped tube used. The distillate collected in step 3 is alcohol ROH. Describe chemical tests and its positive result to show the presence of an OH group in any alcohol. You know the test at PCl5, white steamy fumes. Write equation for the reaction taking place in step 4 with structural formula for organic substances. State symbols are not required. Reaction step 4. What is step 4? Excess dilute hydrochloric acid. Impure benzoic acid crystals are formed. So first you get the sodium salt of benzoate. By adding hydrochloric acid, you get the benzoic acid, right? So sodium salt of benzoate turns to benzoic acid. So C6H5COONA in the presence of hydrochloric. C6H5COOH will be produced along with the sodium chloride. Conversion of salt into the acid by the acid by adding acid. State what should be done to separate the benzoic acid from the mixture produced in step 4 before carrying out step 5. Before the step 5, this is see step 4 to step 5. Go back and check the steps again. Impure benzoic acid forms as crystals in the mixture. Step 5 is recrystallize. You need to have the solid separated, right? So you have to filter it under reduced pressure to get a higher yield of the crystals. Right? Filtration, you can say. This filtration is okay. Like I say, filtration is in the Buckner funnel or reduced pressure. That's more effective, right? Gravity filtration is also fine, but it's quite slow, but that's okay. Fine. Describe the first stage in the recrystallization. You have to dissolve the solid in minimum amount of hot water, hot solvent. Solvent is water here, right? So dissolve the solid in minimum amount of hot water. Why minimum? If you add excess, then what happens? You will not form recrystals again, because it will again heat to evaporate excess water. When there's excess water, recrystals won't form. Right? Why hot solvent? If it's soluble in hot solvent, when the solvent is cooled, crystals will appear. If it is all in under hot conditions and it's cooled, crystals will appear. So you can form the crystals easily by heating or cooling to room temperature. Yeah. The melting temperature of pure benzoic acid is 102 degrees Celsius. State two ways in which the melting temperature changes if the benzoic acid is not pure. Melting temperature, now boiling point will increase, right? When you have impurity, boiling point will increase. Melting point will decrease, right? Melting point will be lower and it will melt over a range of temperatures, not only just lowering. You won't have a sharp melting point. Remember, when the impurities are present, boiling points are going to increase, boiling points will increase, and the melting points will decrease. Boiling point will increase, the melting point will decrease, and then it will melt over a range of temperature. It will not have a fixed value. Okay. There's a question from Kim 31. Can you say the value of melting point is not consistent? Yes, that is fine, but we specifically mentioned that it drops because we know whenever there's an impurity, the boiling point rises, the melting point drops. So that dropping point is important, lowering is important. And if it is not consistent, it will melt over a range of temperatures. That's the second mark. So you have 2 marks given, right? 2 points you should write. Molecular mass of X is 178. Deduce the formula of alkyl group. So let's see. The C6H5 group. Let's find this up to this point without the R, the molar mass. You have 7 carbons, so 12 times 7 is 84. And there are 2 oxygens, 16 plus 6 is 1632, plus there's 5 oxygen. So this part is 121. And the R, to find 178 minus 121, get 57. So what is the alkyl group which has 57? CH3, CH2, 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 right? Okay, because the 4 carbons is 48, 12 times 4, 48, plus you can add the 9 hydrogens, 57. Right? So we don't know. They're asking for the formula for R, so it can be a branch one. So safer to write the molecular formula C4H9. We don't know because it can be, even if you draw a straight strain, it's okay. It's not wrong, but we don't know actually. It might be a branch one. We don't know, right? Use the answer to F1. Draw the structures of the 4 possible alcohols. So you can draw butanol, straight chain, butanol, right? And you can draw a branch now at this point. And then you can draw a branch in the first carbon, OH carbon, CH3, CH, CH2, CH3. There are 3 possibilities so far I have drawn. And then you can draw a tertiary carbon, right? Tertiary alcohol. Primary alcohol, primary, this is secondary. You can draw 3 methyl groups. Tertiary alcohol. Part of the 330 NMR spectrum of X corresponding to the R group contains only 2 peaks. Then of course it has to be this. This has 1, 2, 3, 4 peaks. 1, 2, 3 peaks. 1, 2, 3, 4 peaks, and this is only 2 peaks. You can draw this structure. The carbons are in only 2 different environments. Right? 2 different environments. So structure of X, what is X? The entire molecule. So you draw the structure of the entire molecule here. So you have C6H5, C double bond OO. You have the CH3 groups. You can also draw the benzene ring here. Right? Clear? And that's the question 4. Any questions there? Any further clarifications? Everything's clear? Okay. Right, so we'll take a short brain break and we'll complete the final paper. This is 2022 Jan paper after the break. Right, let's continue. I hope everyone is back. This is a 2022 Jan, the latest paper. I hope you have tried all the questions. A flow chart of series of reactions of chromium and some of its compounds is shown. You add dilute HCl, you get a blue solution. This can be chromium 2. Of course, we know only one blue solution, right? Chromium 2 plus. So this contains chromium 2 plus. And then standing in air, it turns to chromium 3 plus and ammonia, chromium 3 hydroxide, and that will be soluble to form hexamine, hexaamine, chromium ion. Warm with reagent C, yellow solution. It's quite interesting series of reactions. So let's write the formula. Blue solution is that is hexachromium solution. Standing here, it turns to green solution. Again, 2 plus hexachromium 2 plus 1 turns to 3 plus. Green and ammonia, green precipitate. Excess dark green solution is hexamine chromium 3 plus. And then you have warm with the reagent C, yellow solution. What can this reagent C be? You have sulfuric solution E, warm with ethanol, and this is yellow solution, barium nitrate, yellow precipitate. That's right, yes, of course. That's the only yellow solution we have, which is chromate. So solution reagent is acid, right? We're warming with the acid, hydrochloric, for example. You oxidize it in the presence of acid. Chromium 3 plus in the presence of acid turns chromate. And this is chromium sulfate. And then we'll see the rest of it. Yellow solution, barium nitrate. You have barium chromate. Then. Barium chromate should be the yellow precipitate, right? And yellow solution sulfuric. Yellow solution E. Solution E. So that is also solution which we have to. Let me look at the questions. It will be sometimes helpful. They'll give a clue in the question. Hit the found the complex ion of chromium present in solution A. Complex ion of chromium present in solution A is hexachromium 2 plus. Hexachromium 2 plus. And next, precipitate B, chromium 3 hydroxide. Chromium 3 hydroxide. And then identify the reagent C by name or formula. Reagent C. Can he add an acid or is reduction, right? Sorry, oxidation, right? No, this is not the acid. Acid is over here. This is oxidation, correct? A plus to 6 plus oxidation. So this is you can add oxidizing agent. Oxidizing agent. What is oxidizing? Only oxidizing agent we use here, if you remember the theory, yes. Hydrogen peroxide. This is explained in the theory. I explained this. To oxidize chromium 3 plus 2 chromate with the electrode potential half cell values, E cell values, the best is hydrogen peroxide. Hydrogen peroxide. In alkali conditions, yes. Just asking for the reagent. Main reagent is hydrogen peroxide. Conditions are not necessary because they're not asking for the condition. The precipitate D is barium chromate. Barium chromate. and call out the solution E. Now here, what happens is that in the presence of acid, yeah, this is actually oxidation. It should be hydrogen peroxide. But the presence of acid, the chromium 3 plus turns to, chromate turns to dichromate. Remember? That happens when you just add acid. Solution E is dichromate, which will oxidize the alcohol to carboxylic acid or aldehyde. Carboxylic acid or aldehyde, because if you're refluxing it, it's carboxylic. If not, if you're slightly warming, because dichromate is oxidizing agent. That's what reacting with alcohol, the primary alcohol, right? So you need, from that itself, you know, this is oxidizing agent dichromate. The color of the solution is orange. Color of the solution F is F. After reduction, it turns green because oxidizing agent oxidizes the alcohol and itself reduces. Self undergo reduction to Cr3 plus, so it turns green. It turns green at the end. Precipitate D is formed. This question can explain how the precipitate D is formed. Precipitate D is formed. The yellow solution we know chromate, right? Chromate reacting with barium. Barium chromate is yellow. Lead chromate, lead 2 chromate is yellow. Barium chromate is yellow. That's the yellow precipitate. Nothing else it can be, right? Because barium should react with the chromate. Like barium sulfate is white, barium chromate is yellow. That's the first question. This question is about identification of 3 organic compounds X, Y, and Z. A molecule of each compound has only one type of functional group, so it's important to note that one functional group. Each compound contains 6 carbon atoms and 2 oxygens. We have 6 carbons and 2 oxygens. The mass spectrum of X, the molecule of iron peak at mass charge 114. State the molecular formula of X. So 2 carbons, 2 oxygens, 6 carbons. 6 carbons, 12 times 6, 72. 16 times 2, 32. 104, right? So 114 minus 104, you get the hydrogen. 10 hydrogens. So it's C6, H 10O2. Because 6 and oxygen, carbon and oxygens are known. 6 carbons and 2 oxygens. That will be 104. The remaining has to be hydrogen, right? A common element found in many organic compounds. 3 chemical tests were carried out on X. Red is which is 2,4-DNP. An orange precipitate is formed. That means that confirms the presence of an aldehyde or a ketone group. When X is heated with acidified solution of potassium dichromate, no color change. That means it's a ketone. If it's aldehyde, the color change will take place because aldehyde is oxidized to carboxylic acid. So oxidizing agent itself undergo reduction. But it's a ketone, the further oxidation will not take place. When X is added to alkaline solution of iodine, the formation of a yellow precipitate is formed. That means it is a methyl carbonate group. Just for either form, right? I mean, just for the methyl carbonate group is the either form test. You add an AOH and warm, you get a yellow precipitate. I explained what can be deduced about the functional group present in X by the above results. So test 1, you can say test 1 confirms the presence of an aldehyde or a ketone. Test 2 confirms the presence of a ketone group. Test 2 confirms the presence of a ketone group. Test 3 confirms the presence of a methyl carbonate group. Methyl carbonate group. High-resolution proton NMR spectrum of X contains only two singlets. Relative peak areas 3. So these three. One has 3 hydrogens. Other one has 2 hydrogens. Reduce the structure, draw the structure of X. Defined. So there should be a methyl carbonate group for sure. And the 3. So there should be how many? C6H10O2, right? From that, yes. And there should be a CH2 group because it's 2:3. I have drawn 3 carbons, 5 hydrogens, 3 carbons, 5 hydrogen, and 1 oxygen. What is remaining now? The 3 carbons are remaining. Are the 5 hydrogens? No, the 5 hydrogens here. And oxygen is remaining. Methyl carbonate groups. What can we do now? This part is confirmed. Now it says 2 peaks, right? Should be symmetrical, that means. 3:2. How about this one? Let's just try. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. No, can't be. Because it has to be 6 carbons, right? It has to have carbons. What else can it be? So yes, we can have other CH2 in the middle and say 3 double bond or CH3. See, now this is methyl group, 1 peak, CH2, CH2, another peak. 3:2 ratio. It should be bad. It should be symmetrical molecule. How do you know symmetrical? Because that's what we understand from 3:2. That means all the hydrogens and the hydrogens are in 2 different environments. So now check the formula. 1, 2, 3, 4, 5, 6. 6 carbons, 2 oxygens, and 10 hydrogens. So that matches the formula. All of these are singlets because look here. Why CH2 group? These two are one peak, right? Adjacent carbon has no hydrogen. 0 plus 1 is singlet. 1. 0 plus 1 is 1. You can't take these two groups separately. You can't say the adjacent carbon has 2 hydrogens, therefore 2 plus 1 is 3. No, because these two are 1 peak. So you had to consider the n plus 1 rule. You have to consider the entire the peak of the C2H4. Adjacent carbon to the entire peak, not separately. The molecular formula of Y is given. When aqueous sodium carbonate is added to Y, effervescence is observed. Identify the name or formula. That means carboxylic. This is a test for carboxylic. So test for the carboxylic group. You get effervescence in the anticarbonate. So it's a carboxylic group. This is Y is what? The organic XYZ. Yeah. Each 6 carbons, 2 oxygens. They're all isomers, right? Carbons, 2 oxygens. 6 carbons. Yeah, this is the formula is given. C3 NMR spectrum of Y contains 4 peaks that give 2 possible structures for Y. 4 peaks. 4 peaks. Hydrogen carbons are in 4 different environments. Straw carboxylic acid with 6 carbons. 4 peaks. That means there should be a branch somewhere here. 4 peaks meaning? Yes. So 1, 2, 3. No, it can't be that either because 4 peaks. So here you have already 4 peaks. 1, 2, 1, 2, 3. If 1, 2, 3, 4, 5, 6. No, this is wrong. You have 1, 2, 3, 4, 5 peaks. We draw a tertiary one. These all gives 1 peak. 1, 2, 3, 4, 5, 6. We still have 1, 2, 3, 4 peaks. 4 peaks. Any other abilities? We'll see the hydrogens. 9, 10, 12. 12 hydrogens. The structure. 2, 4 carbons. So other than CH3, CH3, we can have like this. CH2, CH3, CH2, CH3. Means we have a CH3 branch. CH2. 1, 2, 3. CH3, you have a CH2, CH3 here. Just we'll try this. 1, 2, 3, 4, 5. We have 5 peaks here. This is wrong. This is wrong. You have 4 peaks, right? 4 peaks. We have 1, 2, 3, 4, 5 peaks. Try and error. Turn on the one and see. The structure. Carbon. So 1, 2, 3, 4. Try this one. 1, 2, 3, 4, 5, 6. 10, 11, 12. Yes. How many peaks here? Analyze the peaks. 1, 2, 3, 4, 5, 6 peaks. It should be how many peaks? 4 peaks, right? But this will give 6 peaks again. Sorry, 2 before also. 6 peaks. If I, okay, we can do this. We can shift the methyl group over here. Shift the methyl group to second carbon. And we have 2 CH2 groups. Yes, and then that's right. Like this. You have a CH2, CH3. CH2, CH3. We have got 1, 2. I use different colors for different environments. 1, 2, 3. These are same environment. 3 and 4. So 4 different environments for the carbon. 4 peaks. Clear? Explain how the low resolution Proton Nmr spectrum of Y would confirm which of the structures D2 is correct. This will have how many peaks in the NMR? All the hydrogen in the same environment, 1, 2, 3 peaks. NMR. 1 NMR. Here is 1, 2, 3, 4 peaks. Right? So each will have different peaks. So this you can say this structure 1 contains 3 peaks. And structure 2 contains 4 peaks. Write the name and write this has 3 peaks, other one will have 4 peaks. The molecular formula of Z is C6H12O2. Infrared spectrum of Z is shown. It is very clear that there's a carbonyl group, and this can be a CH possible, but the OH will have a larger trough, broad band. Let's see. Aldehyde, OH. From the OH, there should be a broad band, but anyway, very strong band there. let's see now. This is at 1750, like 1750. So it can be ester. Yes. Proceed. Analyze the values. Yeah, we know it's ester. It says fruity smell, and you can see here ester's carbon ion vibration is 1750 to 1735. This is 1007, and this is 1008. So it's exactly about 1732 in that range, right? That itself, we know it's ester. And plus, it says sweet smelling, then fruity smell, then is ester. This is the identity of the functional group present in Z. So Z is ester functional group using all the information given, relevant wave numbers. So C double bond O of ester is between 1750, 1735. That is how we the sweet fruity smell, we can say it's ester. And this is the IR spectrum, this value, but other one is a carbon, the CH 3000 is difficult to use that one. So you can first mention the fruity smell confirms it's ester. And the carbonyl group, the chemical, I mean the wave number of the carbonyl group confirms that it is carbonyl group of an ester. The high resolution proton NMR spectrum of Z contains 4 peaks. Peak J has the highest chemical shift, showing that the proton environment is close to the electronegative element. J has the highest chemical shift, and that will electronegative element. Okay. How does display structure of Z labeling the proton environment responsible for each peak? Now, this is any idea about the number of carbon, hydrogen? That dimension is all same, all isomers. No, we don't know that, right? So anyway, let's see. This is ester. You have J. That's just important clue there. J is a highest chemical shift, showing that this proton is environment attached to electronegative. So that means this has to be the J part, this carbon over here. Because if you have the carbon to the carbonyl group, the carbon to the carbonyl group is not so electronegative, right? Because the reason is that oxygen is more electronegative than carbon. So this is that J they are referring to, right? So the hydrogen attached to this should be attached to 5 carbon atoms, right? Here it says septet. So that means have adjacent carbon should have 5 carbons, 5 plus 1. Yeah. Yeah. The question arises, what's the septet? It is 6 or 7? 7, right? It's 7. subject is 7. That confirms that this is a CH, this carbon. I've been draw the display formula here. Carbon over here has to group like this. Although this is J, because attached to the electronegative, and that should have this set that is 7. Adjacent 3 plus 3, 6 plus 1, 7. That's the only possibility, right? And this should split into doublet. This has to be L because adjacent carbon has only one hydrogen. That has to be a pKal. And then you have a CH2. Then you have J and L. You have quadruplet and triplet. Quadruplet meaning 4. That means this should be the quadruplet because it's CH3 here. Should be the quadruplet, which is K. Adjacent carbon has 3, 3 plus 1, 4, and this has to be the triplet. Adjacent 2, 2 plus 1. Yeah. That's question 2. A student investigated the kinetics of the reaction between bromide ions and bromate ions in aqueous acid. Determine the rate equation for the reaction. Student varied the concentration of bromide ions, bromate 5 ions in an acid in turn. The effect of the concentration of bromide ions was investigated first. At 10 cm cube of 0.005 potassium bromate 5, 15 of acidified methyl orange indicator solution, and 5 of 0.0001 of aqueous phenol to a beaker labeled P. Prepare the contents of the beaker Q for run 1 as specified in the table. Pour the contents of the beaker Q into beaker P and start. What happens here? Q contains, what is Q? This Q here, this is P, contains phenol, and you have potassium bromate and acidified methyl orange indicator. Prepare the contents of the beaker Q for run 1 as specified in the table. This is a table. You have KBr and water. Q is a KBr solution. You have it different concentrations. You can see total volume is kept as 10. As the volume of KBr decreases, volume of water increases. And then pour the contents of the beaker P, Q into P. So the bromate 5 reacting with bromine in the presence of acid is what happens here. Bromine will be produced, right? So acidified potassium bromate 5 contains BrO3 minus. Acidified methyl orange indicator will have plus signs, and a phenol, when you react with this, what happens is that when these two, P and Q, reacts, it forms bromine. Bromine reacts with the phenol to form a white precipitate. So pour the contents of the beaker P back into the beaker Q and place the beaker Q on a white tile. Stop the timer as soon as the mixture turns colorless. Because it turns colorless and forms a white precipitate. Right? 2,4,6-tribromophenols is the white precipitate, and the color of the orange brown disappears. Repeat the steps 1 and 4 for the remaining runs. Okay. So KBr different concentrations are given. Give one reason why the contents of the beaker P are poured back into the beaker Q in step 3. In step 3, P are poured into beaker Q instead. Q is what? Q is KBr. Pour the contents of the beaker Q, KBr into the beaker P. P is that phenol with all this potassium bromate and acidified methyl orange. And start the timer. Pour the contents of the beaker P back into the beaker Q. That means you are just mixing it like your Q to P, P to Q. That's to ensure proper mixing, right? Reactants mix well. It's like basically other than using a glass or just you're mixing one beaker to the other beaker, like just mixing. Reactants mix well to ensure reactants mix well. That's the only reason. Methyl orange indicator is bleach colorless by bromine. Under experimental conditions, the reciprocal of the time taken for the methyl orange to be bleached is proportional to the initial rate. Explain why phenol is added to the reaction mixture. The phenol is added to the reaction mixture to react with the bromine because bromine reacts with the phenol to give white precipitate, right? And then what happens then? The remaining bromine will react with the methyl orange and it will bleach the methyl orange. It turns colorless. Now see, look at the percentages. Phenol is a very, very small amount, right? 0.0001 compared to methyl orange. Compared to methyl orange is 15, and this is 5 cm cube of 0.0001. Compared to potassium bromide, it's a very small percentage concentration. So this little bit of phenol is added to react the initial bromine which is produced. Otherwise, it will be a problem because when a little bit of bromine is produced, then the methyl orange will turn colorless. So you can't identify the color change because it will be a quick reaction. So by adding phenol, what we do is we just simply delay the reaction for a while, and that delay is constant for all. This delay is important for us too, because in that case you get a greater time, the percentage error, the time will decrease, and delays enables us to find the color change very clearly. Basically, you're prolonging the reaction by destroying a constant amount of reactant which is produced, the product which is produced. That's why I did the phenol first. Similar thing we did in iodine thiosulfate, if you remember. We had thiosulfate, little bit of thiosulfate to delay the purple precipitate of fine iodine reactive starch, because that is important, right? That is important. This is done to delay the formation of the color change by the reaction of the bromine, initial bromine with phenol. Initial bromine reacts 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 with phenol and delay the color change. Therefore, color change will not occur until a fixed amount of bromine is produced. Therefore, color change does not occur until a fixed amount of bromine is produced. I'll give the color of the reaction mixture before it turns colorless. That means it turns the white precipitate first. Initially, phenol reacts. Methyl orange turns bromine is brown, and then it will turn methyl orange, because initially there's acid, right? Methyl orange will turn to presence of acid, it turns red, and then it turns colorless. So red and colorless here. Question says at which point before it turns colorless, methyl orange will, before it turns colorless, where it turns colorless, that is when you add the mixture, right? Before it turns, because it turns colorless because bromine is a bleaching agent like chlorine. You might wonder why bromine does change the color of the methyl orange, because bromine is just like chlorine, it's a bleaching agent. So it will bleach the color, right? The thing is, before that, there is acid here, right? There'll be a small color change to the acid, red color. It turn to red and then it turn to colorless because of the presence of acid, right? Yeah. Give the reason why the temperature is measured in step 4, because we have to make sure the temperature is constant, because we are changing the concentration of KBr. So because temperature affects the rate, so we had to make sure the temperature is kept constant throughout. The temperature should be kept constant throughout, as the temperature affects the rate. Temperature should be kept constant throughout, as the temperature affects the rate. As a question, can you explain the color change again, please? Now, the bromine is orange brown, right? Bromine is orange brown. So in this reaction, it produces bromine. When you mix all, it produces bromine, right? And bromine, what happens? Will react with the methyl orange. Bromine is a bleaching agent. It will turn colorless, right? Because it will bleach the, the bromine. So now they're asking for intermediate color. So only thing we can think of is that there's methyl orange indicator, acidified methyl orange. So there can be a color change of red color because methyl orange is in acid red, right? That can be because of the presence of acid, methyl orange can turn to red, and then it will turn to colorless. There can be intermediate color change of red color. Anything else here? Bromide, bromate, yes. Yeah. There's no other color change, right? You can't think of anything else because bromine is orange brown, it turns colorless. When you add phenol, it gives a white precipitate. And then only thing we can think is methyl orange in a little bit of H plus. That is the acid color is red. Results are shown. You can find the values here. 1 upon 48, 0.021, 0.0208, so 21, and 1 upon 64 is 0.015. 0.015 means 0.016 because reason 156, right? So you can say 1.6 is 0.016. Plot a graph of 1 upon T against the volume of KBr. What is 1 upon T? Is the rate. Right? 1 upon T is the rate. 1 upon time. So what should be the rate? Which axis? Y axis. Because you're studying how the volume of KBr affects the rate. Studying how the volume of KBr affects the rate. So volume of KBr should be your x-axis, and the y should be 1 upon time. And you plot the graph, you have to make sure at least 2/3 the value should, you should spread the values so that the 2/3 of the graph paper should be covered. Two-thirds should be covered. What type of plot is this? I'm going to plot the graph. Straight line or a curve? It should be a straight line, most probably, because that's how the straight line goes to the axis, the origin. We go to the origin. To the origin. Any anomalous points? Can you please mark it on the graph? This is just a rough sketch. You had the best fit line you should draw. And any anomalous points, please mark it on the graph. Yeah, you can just mark the anomalous points if you're done. Okay, somewhere here. We are here the anomalous point. Below the line. Set by the volume of KBr is proportional to the concentration of bromide ions because total volume is kept constant. Because we keep the total volume constant, the volume of KBr is proportional to the concentration because just because you're keeping the total volume constant, see, always total volume is what? Is 10, right? Yeah. Previous page. And see, total volume is 10. So when you increase the volume of KBr, in other words, you're increasing the concentration of KBr. Because total volume is kept constant. So proportional because the total volume is kept constant. Set the order of reaction with respect to bromide ions using a graph. That means you can see as the volume of KBr increase, the concentration should increase simultaneously. If volume is x here, volume is increased to 2x, the rate is y, and the volume is double, the rate should double. If that's the nature of the graph, then it's first order. If the graph is like this, when volume is doubled, if the rate is increased by 4 times, then it's second order. So to check your graph, this is simultaneously increasing first order. Right? First order. Is it first order or second order? The straight line, so I don't know how the straight line because we didn't plot the graph. Let me know if it is first order or second order. If just say, see, analyze doubling of the concentration, doubling of the volume, if the rate is double, then it's first order. If not, second order. It's first order, right? After investigating the effect on the rate of the concentration of bromate, 5-ion, and the concentration of hydrogen, obtain the graphs here. This is both first order and this is second order. This is second order, plus second order. So rate equals rate constant, PR minus, right? PR minus is first order, PRO3 is first order, H plus is second order. That's question number 3. It is a long question paper. There's only one more question here. This question is about the preparation of phenylamine by the reduction of nitrobenzene at 2.1 cm cube of nitrobenzene, 5 grams of granulated tin, and 10 cm cube of conc hydrochloric acid to a round bottom flask. Add a few anti-bumping granules to the flask and heat the contents under the reflux for 15 minutes. Leave it to cool, and then dissolve 7.5 grams of sodium hydroxide and 10 cm cube of distilled water. Add to the flask initial precipitate forms before dissolving. Add 15 of distilled water to the flask and steam distill the contents, collecting the polydistillate in a conical flask. Add 3 grams of powdered sodium chloride to distillate to dissolve before transferring the contents of the separating file. This is to absorb all the moisture to the NaCl. It's not a drying agent, but NaCl helps to remove the water to another separate layer. Add 8 cm cube of either to the funnel and shake occasionally, revealing the pressure. Allow the layers to separate and discard the aqueous layer before transferring the ether layer to a clean flask containing few pellets of potassium hydroxide. Again, this is to remove the water. Decant the contents of the flask from step 6 pear-shaped flask and distill the remaining contents of the pear-shaped flask, collecting the fraction volume between this range. Nitrobenzene toxic, molar mass density and the boiling temperatures are given. Phenylamine inhalation toxic, that means it will carry out in a fume cupboard. It is highly flammable, that means you should not keep any open flames. Give 2 reasons why gloves should be worn in step 1. Because in step 1, what we do in step 1, see, nitrobenzene, concentrated hydrochloric acid is corrosive. right? Conc hydrochloric acid is corrosive. And nitrobenzene, we know it's see, nitrobenzene, thin absorption. So wearing gloves is important because if you touch the nitrobenzene, it absorbs to the skin. It's a carcinogen, cancer causing. So HCl is corrosive. Nitrobenzene is absorbed to the skin, so you have to wear gloves. Say the role of the tin in the preparation. Tin is a reducing agent, right? Here we know the conversion of nitrobenzene to phenylamine. Zinc is used as a reducing agent. Zinc HCl, reducing agent. Zinc is a reducing agent. Suggest the name of formula, the identity of the initial precipitate form in step 3. Step 3. Sodium hydroxide, distilled water, initial precipitate form. What is the precipitate here? This is tin. Tin with hydrochloric, tin 4 chloride, or tin 2 chloride, say. Sodium hydroxide, precipitate is formed. Let's see. It has to be precipitate of tin. So here, tin will react with hydrochloric. Tin is a reducing agent. That means itself undergo oxidation. It has to be tin 2, right? Because tin 2 plus can be oxidized to tin 4 plus. Right? Tin is oxidizing agent. Sorry, tin is a reducing agent here. Itself undergo oxidation. So tin reacting with HCl, what is formed is tin 2 chloride. So tin 2 chloride reacting with alkali, you get tin 2 hydroxide. So the precipitate here is SNOH twice, tin 2 hydroxide, because tin is reducing agent. That means itself should undergo oxidation. So tin can't be 4 plus because it's a high oxidation state. So 2 plus should go to 4 plus after upon oxidation. So the tin reacting with hydrochloric, it will form tin 2 chloride. Tin 2 can be further oxidized to tin 4. As a question, repeat the answer for B1. Role of the preparation. Tin is a reducing agent. We know it's reduction, right? Tin HCl is a reduction of phenylamine to aniline. State why the distillate in step 4 is cloudy. This is organic product. The organic product will be cloudy because water is. We have discussed this before, right? The organic product will be cloudy because of the presence of water. That will drive and a drying agent and remove the water. Cloudy due to the presence of water. That is why sodium chloride is added to this. That's a very important thing because sodium chloride, when you add, its ionic substance is basically helps to pull the water molecules trapped within the organic layer. Now, this is not drying agent. NaCl is not a drying agent. Drying is added later on, right? Because before you add drying agent, if you add NaCl, what happens? It basically dissolves the water and pulls the water into the aqueous layer. So that will enhance the separation of the layers, right? So no, it's not a drying agent, not to remove water. It helps the separation process, right? So sodium chloride, it's not dissolve, it's not removing water. It basically pulls the water into the aqueous layer. Sodium chloride attracts the water molecule and separates into the aqueous layer. Attracts the water molecules and separates into the aqueous layer. Resulting in effective separation. Results in effective separation. Draw a label diagram for separating file at the end of step 5. So you need to know the two solutions, more dense and the less dense one. Step 5, you see the densities of the organic layer, which is phenylamine. What is the last step 5? No? Step 5. So step 5, what do you have in step 5? So the implied is so dissolved. Ether is added. Funnel occasionally relieving the pressure to the layer. So ether is there. Ether is the organic layer, because organic solvent will go to the ether, right? So you don't have the phenylamine. Phenylamine is produced at the last stage. So you have the organic substance dissolved in the ether. Clear? It is a solvent. Like what is a solvent? Ether is a solvent. Ether dissolves the organic substances. So here you have organic solvent, which is mainly ether and water, aqueous. Ether is less dense, right? So it should be above. Organic should be above aqueous layer. Less dense. This is the organic layer. And this is the aqueous layer. Clear? I hope that is clear, right? That is step 5. State how you would relieve the pressure. This is we have discussed before. You basically turn the separating funnel and open. While shaking, you open the tap. So basically, you turn the separating funnel or invert the separating funnel, open the tap while shaking to release the pressure buildup. Such is one reason for adding pellets of potassium hydroxide. Now, potassium hydroxide can absorb water. Potassium, not like sodium chloride. Sodium chloride is not a drying. Potassium hydroxide can act as a drying agent because it will absorb moisture. Right? State how the mixture would be heated to distill off the ether in step 7. Now, ether is flammable. It's flammable, right? Be careful. Now, ether using indirect heat source, highly flammable. Can you see? Ether is highly flammable. So you have to use indirect heat such as oil bath. Yes, water bath is also okay because boiling temperature is 35. So what is the purpose of heating? Distill off the ether. Heated to distill off the ether. So you can use a heating mantle, indirect heat source. Water bath is fine. Right? Say, do not use direct heating as ether is flammable. Not use direct heating as ether is flammable. Instead, use indirect heat source such as oil bath, water bath, or a heating mantle. Water bath is okay here because of the boiling points are being less than 100 degrees. Aqua is a mass of phenylamine formed in preparation. Limiting reagent is nitrobenzene, and overall yield is 43%. So you have nitrobenzene, phenylamine. Right, the first step, is to what data is given? It's 43%. So let's see any mass of or density of nitrobenzene is given here. Yes, 2.5 nitrobenzene. So 2.1 nitrobenzene. 2.1 grams of nitrobenzene. So you can first find the 2.1 grams of nitrobenzene, right? Sorry, cm cube. So to find the mass first. Find the mass first. 43% of that. So let's find the mass. Mass of nitrobenzene. This is density equals mass over volume. So mass equals density times volume. Volume we know, nitrobenzene density is 1.2. 1.2. So this multiplied by 1.2 as 2.52 grams. 2.52 grams. You can now work out the moles. Moles of nitrobenzene, because the rate you can use the moles of it to find the moles of phenylalanine. 2.52 divided by the molar mass. It's already given in the question. Into calculate 93. Sorry, nitrobenzene is on 123. This is divided by 123. You get the answer as 0.020. 0.020 moles. So once you find that, you have to find the percentage dissociated moles of phenylalanine. That is 43% yield, right? Of this, 43% of this. So moles of phenylalanine is 43% of this, 0.020 into 43%. 0.020 into 43 is 8.6 10 to the power minus 3 moles. 8.6 10 to the power minus 3 moles. Then you multiply that by the molar mass to get the mass. Mass of phenylalanine. Molar mass is also given in the question. 93 times 93, you get as 0.7998 grams. Right, so what's the question now? So all information, calculate the mass of phenol quantity. No, we took 43%, right? 43%. 43%, right? I took 43%, not 100%. If you need to find 100% yield, then we don't need to this simply multiply this by 93. I took 43 out of that. Understood? If you want the 100% yield, then you have to just not do this. You can multiply this value by 93. We don't need to do that because you can't take 100% yield here because it's not 100% yield, it's 43%. You've got the 43% of phenylalanine because you have 0.02 moles of phenylalanine, right? Out of that 0.02 moles of phenylalanine, only 43% dissociates. So this is the amount which actually reacts, 8.6 in power minus 3. That is the amount which dissociates, and that's the amount of phenyl NMR which is produced. That into the molar mass. If you want, you can find 100% first and then find for 43%, but that's a long extra calculation. No? Additional time consumption and this additional unnecessary step. Unnecessary step is also fine. Clear? This question is a long experimental procedure, but that doesn't affect. It doesn't matter. You know, you're not going to question all. They didn't question all the steps, right? Only few steps. Any questions further? So with that, we conclude the latest paper. From next lesson onwards, we'll be continuing our paper 5 discussion. And I have completed the new syllabus 2019-2022 new syllabus paper 6. So before the paper 6 exam, if time permits, we'll do some of the old syllabus papers as well. So next week, we'll be discussing 2019. May, I think Jan paper 5 we just completed last week. So we'll discuss 2019 May paper 5 in the next session, and that will be on Wednesday. Right. So with that, I'll conclude.